All right, so example 1. For this one, we're going to take this function, x minus 5 divided by x squared plus x minus 2. Now, to find my domain, what I want to do is take all of the x values where the denominator, x squared plus x minus 2, is not equal to 0. Well, okay, it would help if I could solve that equation, x squared plus x minus 2 equals 0. Then I would identify what values I need to avoid or exclude, right? So what I'm going to do is actually take this polynomial, take this rational function and factor the polynomials. The numerator is linear, so that can't be factored at all, but the denominator can definitely be factored. This step here of factoring the numerator as much as you can and factoring the denominator as much as you can is often the first thing you want to do with a rational function if you're going to learn anything about it. So the denominator here factors as x plus 2 times x minus 1. So I've got to make sure that x plus 2 times x minus 1 is not 0, which means I have to avoid negative 2 and positive 1. So this is the set of all x's such that x is not equal to negative 2 and x is not equal to positive 1. Now, writing that in interval notation, which is usually how we want to express it, we're going to take all of the numbers less than negative 2, and then we're going to take the numbers between negative 2 and 1, then we're going to take the numbers that are bigger than 1, and those three intervals with open endpoints, not including the negative 2 and not including the 1, union that together. So this is three different intervals connected, or combined together there. That's my domain. So next, zeros. 0 or zeros. In this case, there's actually only one. We just got to take the numerator and set it equal to 0. X minus 5 equals 0, and that gives me a 0. X equals 5. I should be putting boxes around my answers. So this was my domain answer. And that's my answer for zeros. X equals 5. So there's only one 0. That means it's going to cross the x-axis at 5. Vertical asymptotes. I'm going to start abbreviating. Vertical asymptote as VA and horizontal asymptote as HA. So for this one, same thing that we kind of did before. We got to take the denominator, x plus 2 times x minus 1, set that equal to 0, and that'll get your two answers. And so we have x equals 1 and x equals negative 2. And those are the two vertical asymptotes for this function. Now, this is the moment where you might want to check. Remember that if the numerator and denominator are both equal to 0, you might have a hole. So let's check to see if we have any overlap. We said these were zeros and these were vertical asymptotes. If we had a number that was the same, then actually it would be neither, and we'd have to cross it out and say, never mind, actually we've discovered there's a hole there. Usually. That's pretty much how it works. I'm saying that because sometimes you can actually end up with a vertical asymptote in that situation if the multiplicity is higher in the numerator than it is in the denominator. So it's a little more complicated than I'm letting on, but we're not really going to encounter that very often, so I'm not going to go into details. Okay, so in this case, since the degree of x minus 5, the numerator is 1, and the degree of the denominator, x squared plus x minus 2, is 2, we are in which case? Let's see, the denominator is the one with the higher degree, so that would be case B right here. Degree of P is less than degree of Q. Case B. So that means we do have a horizontal asymptote in this case, and it is y equals 0. I will say one thing about why that is, okay? We're done with this example now. But when you have a situation where your denominator has a higher degree than the numerator, like in this one, what that means is as x approaches either positive infinity or negative infinity, when x gets really, really big, the denominator essentially overpowers the numerator. It is growing faster, like so basically, like if you have a line, then that does not grow as fast as a parabola, which in turn does not grow as fast as a cubic. So this is like x squared, x cubed. then x to the fourth would be like that, x to the fourth. So the idea is the higher the degree of the polynomial, the faster it grows and the more powerful it is when x gets really large. You can actually prove that the limit, sorry, not the limit, that you can prove that, you can prove that it's going to be approaching 0 with a little bit of sort of algebra manipulation. That's something I usually reserve for a calculus class. So I think this explanation of like basically the numerator gets bigger than the denominator will get much bigger than the numerator, relatively speaking, when x is large because of the sort of rate of growth being higher. That explanation will serve us good enough for now. But if you're curious and you want to see the details, you can always let me know.